I'm Joshua Orlando. I'm the project engineer too for connected vehicles, working in the ADAS segment.
Okay.
So my two main projects are a Department of Energy project in partnership with Michigan Tech, Borg Warner, Navistar, TTS, and the goal there is a cohort driving, and the main goal for that is actually reduction of energy consumption for the overall cohort, multiple different powertrains, all connected agents, utilizing vehicle connectivity to optimize powertrain and velocity profile to essentially mitigate emissions and reduce overall energy consumption. As of late, we just had an update meeting with them where we're showing an average of about 15% for a full vehicle cohort with full size truck, class 8 heavy duty as well as light duty vehicles. Then the other project is Canoe, which we are constantly moving forward and working through overall system validation of a L2 plus ADAS system, and simulating all these different scenarios in order to evaluate and validate the software before release. So originally, I was hired in simulation. With the moving around of reorganizing the company, I actually worked directly for a chief engineer who during the reorg left. So in terms of simulation, I've always been a large proponent of taking validation from vehicle and test fleets into simulation applications where you can have multiple different variations of scenarios to evaluate software without actually having a person in the vehicle. Additionally, you can create edge cases, generate edge cases for all these different types of maneuvers, be it ADAS or powertrain or calibration. So with that, when you move into the simulation world, you can do multiple test runs at your desk rather than being in a vehicle, traveling around trying to find these different scenarios or make them happen with either, dummy vehicles or a scenario that you kind of have to create with multiple vehicles on the road, where you can take this into the simulation world in which you can just create it, replicate it, change a bunch of additional parameters, and then at that point you also have a very predictable application to actually know what's going to happen in the scenario. There's no outside variance that will occur. There's a large push for all these battery electric vehicles, really pushing the platform forward. With that, there has been newcomers in the field of building vehicles and actually selling vehicles. With that, it is really hard to compete at that level with an institution that is owned by 3 or 4 agents, I'd say. And in that space, to get ahead or to fill in some of the area, we as a company, utilize some of these simulation technologies to bring us forward to help with any of those, either calibration, software development, or validation of the system that would really mitigate the additional effort of in-vehicle calibrators. Although necessary, they could still be, front-ended by simulation to pull the software forward and the calibration forward to a point where it's in a good spot to be in a vehicle, which would then in turn have to have a reduced size test fleet, but still be able to meet, key metrics that you want to accomplish. Predictive energy management, or PREM, is the utilization of connectivity to create a horizon for your vehicle agent, however you want to call it. It could be an industrial factory, it could be a school, it could be the grid, it could be a vehicle, And at that point, you want to create a predicted horizon of what the next 10 seconds or 200 meters or any type of future bounds of the agent, to then optimize a portion of that agent for energy consumption. So if you look at the aspect of a vehicle, while you're driving on the road, you can utilize sensors, vehicle-to-vehicle connectivity, vehicle infrastructure to generate a prediction horizon for your vehicle. From there, since you have that prediction horizon of what may happen, you interpolate that into optimizing either the powertrain or the vehicle velocity for energy consumption. And it can be pulled past energy consumption at that same point, in terms of, if you look at a fuel cell, how often can you, or how quickly can you change how much request for energy is coming from that fuel cell, the ramp up time, and just overall flow of electricity and hydrogen in the system. It's not immediate. So you have physical limitations of the system that you have to abide by, and you can optimize just that example with a prediction horizon and knowing what's coming next, and start to get your system in an efficient and feasible area for the next time step in which you're going to apply those conditions. In retrospect, with the DOE project, we're utilizing connectivity for multiple different powertrains, none of them fuel cell based, but we have EVs, hybrids, and IC engines. So a couple examples that we look to optimize on that given project would be velocity, gear state or shift cycles, and then finally going towards, torque split of a, hybrid powertrain between the engine and the IC motor and the E motor, which in turn would reduce energy consumption of the overall forward.